Do you see what I see? What mathematical objects do you see? What are their properties? What is their behaviour? Pause the video now and capture these objects and their behaviour on paper as best you can. How did you go? Did you see 6 mathematical objects, 3 points, A, B and C? How about 3 line segments, AB, BC and AC? Did you see that the position of one of the points was constant? It did not move. And that the position of the other 2 points varied. They moved horizontally. Did you see that one of the line segments, BC, seemed to be of constant length, while the other 2 line segments, AB and AC, varied in length? Did you see that the length of the line segments AB and BC could be added to obtain the length of AC? To confirm these observations, some more information can be revealed. This information about the location of points A, B and C at different stages of the animation confirms our observation about the points, with point A fixed in position and points B and C varying as they move left to right. The information about the points also confirms our observation about the line segments. From the information revealed, it seems that BC has a constant length of 2 units, even though B and C move, and that the lengths of AB and AC vary as points B and C move. How did you go capturing our dynamic diagram on a static piece of paper? Not such an easy thing to do. Here are some attempts by others to capture these ever-changing objects. Each attempt has dealt with the challenge of representing AB, a line segment of varying length, in different ways. The broken axis symbol is used in the first attempt, looking like a bouncy spring moving left and right. The second attempt has those 3 dots, which traditionally represent a process that continues. The third attempt represents the varying length with the variable x, and contrasts it with a constant length labelled with a constant 2. This makes sense because variables vary and constants are constant. Based on that thinking, the other line segment with varying length, segment AC, can be labelled with the expression x plus 2, which is a varying quantity 2 more than x in length. Which of these do you like? Did you come up with other ways to represent variation on your page? Now that we have this clever way to represent variation using a variable, as well as some nice diagrammatic techniques, let's take a look at this dynamic diagram. Pause the video now and capture on paper the mathematical objects that you see and the way that they do or do not vary. How did you go? As well as now seeing 6 points, 2 constant and 4 varying, you probably saw up to 9 line segments, some fixed in length, some varying, as well as a couple of rectangles. Along with the line segments that we have already labelled with length x and length 2, we now have line segments with a different constant length that looks to me to be length 3. Did you see 3 times x? Can you see 3 times 2? These labels represent the area of rectangles ABEF, which varies according to the rule 3x, and the area of rectangle BCDE, which does not vary and is equal to 3 by 2, or 6. Now, let's double up on line segment AF, reflecting F about AC to create the new point F'. While we're at it, let's reflect D about AC to create D', giving us this dynamic diagram. Pause the video now and add to your previous diagram, Label the new mathematical objects that have been created. What is the relationship between these new objects and the ones studied previously? How did you go with rectangle ACD''F'? I labelled its width as x plus 2 by looking at the length of the line segment FD, which is the same as the length of the line segment F''D'. From this width of x plus 2 and a height of 3, I labelled the area of ACD''F' as 3 by x plus 2. Did you do something similar? How does this new rectangle ACD''F' relate to the object studied previously? Well, due to the nature of the points D' and F', the rectangle ACD''F' is a reflection of the rectangle ACDF, and so these rectangles must be of equal area. Rectangle ACDF is comprised of rectangle ABEF, which we have labelled as having an area of 3 by x, and the rectangle BCDE, which we have labelled as having an area of 3 by 2. As such, the area of rectangle ACDF must be the sum of these two areas, so it can be represented as 3 by x plus 3 by 2, which can also be written as 3x plus 6. Based on the equality between rectangles ACDF and ACD''F', this dynamic diagram, where x takes a range of values, convinces me that 3x plus 6 is equal to 3 by x plus 2 for all the values of x that have been considered. A statement like this is called an identity. Mathematical identities like this are statements which are true for all values of x, as this one is, which we know based on the diagram from which it came. This identity is an example of an important piece of mathematics called the Distributive Law of Multiplication. This law is so named because the multiplication by 3 can be seen as being distributed to the individual terms within the brackets x and 2, resulting in the terms 3x and 6. This process is sometimes referred to as expanding brackets, but this description of the process does not emphasize that it is specifically the operation of multiplication that can be distributed in this way. Most operations, including addition and the taking of a square root, cannot be distributed in this way. Now take a look at this dynamic diagram. Pause the video now and capture on paper the mathematical objects that you see. Pay particular attention to the lengths of line segments and the areas of rectangles. How did you go, capturing all that variation? I used 3 variables, x, y and z, because there seemed to be 3 lengths that varied in 3 different ways. Based on those variables, the line segment D''F' has a length of x plus z, as its varying length is always equal to the sum of the varying lengths of AB, represented by x, and BC, represented by z. Did you have something similar? Now let's look at those rectangles, starting with ABEF. Now that AF is varying with length y, this area is no longer 3 by x, it is y by x. In a similar way, rectangle BCDE has dimensions y high and z wide, so its area is y by z. Looking at the area of rectangle ACD''F', as it is y high and x plus z wide, its area must be y by x plus z. Based on the thinking that we have done about the rectangle ACD''F' as a reflection of rectangle ACDF and their equal areas, we can say, based on this diagram, that y by x plus z, the area of rectangle ACD''F', is equal to y by x plus y by z, as the area of rectangle ACDF is made up of rectangles ABEF with area y by x and rectangle BCDE with area y by z. This identity, true for all the values of x, y and z that we have observed in our animation, is another representation of the distributive law of multiplication. And now, a final task. The distributive law of multiplication can be applied to make statements like the identity a by b plus c plus d equals ab plus ac plus ad. Have a go at drawing a diagram that captures the truth of this identity.